Today we're going to talk about sinusoidal forcing. Before we do so, let's review some ideas from before about forced harmonic oscillators. Recall back in lesson 13 that we introduced second order linear equations with constant coefficients. That is d squared y dt squared plus p times dy dt plus q times y equals a function g of t. This equation is said to be homogeneous if the right-hand side, that is g of t, is identically zero. Otherwise, we said that this equation is non-homogeneous. When the equation is homogeneous, we found in lesson 23 an algorithm to find the solution. First, compute roots lambda of the characteristic polynomial lambda squared plus p lambda plus q. Second, compute the general solution y of t equals k sub 1 times y1 of t plus k sub 2 times y2 of t in terms of functions y sub 1 and y sub 2 as listed on your screen. And third, determine the constants k1 and k2 by specifying the initial conditions. We're left here with a couple of motivating questions. First, how do we find the general solution for a non-homogeneous equation? And second, are there any real-world scenarios we can apply this to? To answer the latter question, we found a couple of real-world scenarios in which we can use the second-order equation. As a first example, remember back in lesson 12 that we considered a mass m attached to a spring of length L. We assume that there are four forces acting on such a mass. First, the force of gravity. Second, a restoring force coming from the spring. Third, a damping force, meaning that our mass may be in a viscous fluid. And fourth, an external force. If we denote y of t as the displacement of the mass from our equilibrium length, then we find that this function y does satisfy a second-order equation. If there is no external force, we call this an unforced harmonic oscillator. Otherwise, we call this a forced harmonic oscillator. For the second example, we go back to lesson 14, where we introduced an electric circuit. Let's denote Q as the charge and I as the current. We assume that our electric circuit has four components. First, an inductor, in which case the voltage is proportional to the derivative of the current. Second, a resistor. This is a component that reduces the electric flow. According to Ohm's law, the voltage across a resistor is proportional to the current I. Third, we assume that there is a capacitor, and the voltage across the capacitor is proportional to the charge on the capacitor. And fourth, we have an electromotive force, such as a battery. If we denote Y as the voltage across the capacitor, then again we find a second-order linear equation. In this case, we call this an RLC circuit for resistor, inductor, capacitor. In the last lesson, we also found how to solve a second-order linear equation which isn't necessarily homogeneous. The idea is that there exist three functions, y sub 1, y sub 2, and y sub p, such that y sub 1 and y sub 2 are solutions to a homogeneous equation, and they can be read off from the table that you see here on your screen. Next, y sub p is a particular solution to the homogeneous equation, so that the general solution to our non-homogeneous equation is y of t equals k1 times y1 plus k2 times y2 plus y sub p. Notice that if we can find just one solution, y sub p, to the non-homogeneous equation, then we can use this table you see here on your screen to find the general solution. This is exactly what we're going to discuss today as we go over sinusoidal forcing. Our quest is to try to find at least one solution y sub p, and then use this previous proposition to find the general solution. To this end, let's consider a second-order linear equation, d squared y dt squared plus p times dy dt plus q times y equals g of t. We'll consider a couple of special cases about our function g of t. First, let's assume that g of t looks like an exponential, that is k times e to the rt for some constants k and r. If r is not a root of the characteristic polynomial, then a particular solution, y sub p, is a times e to the rt for some constant a, which is k divided by r squared plus pr plus q. Next, let's assume that g of t looks like capital K1 times cosine omega t plus capital K2 times sine omega t. First, we observe that we can express this function g of t as capital K times cosine omega t minus theta, where capital K is the square of the sum of the square root of the sum of the squares, square root of k1 squared plus k2 squared, and theta is the arctangent of k2 divided by k1. If a certain expression does not equal to 0, then a particular solution, y sub p of t equals lowercase k1 cosine omega t plus lowercase k2 sine omega t for some constants k1 and k2. Moreover, we can express this particular solution in the form capital A times cosine omega t minus phi, where capital A is capital K divided by the square root q minus omega squared plus p omega squared. And phi equals theta plus the arctangent of p omega divided by q minus omega squared. We'll use this now to introduce a couple of definitions. First, whenever we say our g is equal to capital K times e to the rt, we will call this exponential forcing. Notice that a particular solution is also an exponential. On the other hand, if g of t is capital K times cosine omega t minus theta, we call this sinusoidal forcing. Notice that a particular solution is also periodic. Moreover, we define the angular frequency as omega, the period, capital T, as 2 pi divided by omega, and the phase angle as phi. You'll notice a curious byproduct of this proposition. The phase angle theta is different in general from the phase angle phi. We're going to discuss this in a bit more detail coming up in lesson 29. First, I'd like to explain why this proposition is true. There's really a bit more algebra happening here behind the scenes that'll be more useful than just simply writing down a big proposition. First, let's say that we have exponential forcing. That is, we'll assume that g of t is capital K times e to the rt. If we guess a particular solution in the form capital A times e to the rt, then we can express y as a times e to the rt, the derivative y prime as r times a e to the rt, and the second derivative y double prime as r squared times a times e to the rt. This means that d squared y dt squared plus p times dy dt plus q times y will be equal to r squared plus pr plus q times capital A times e to the rt. If we assume that r is not a root of the characteristic polynomial lambda squared plus p lambda plus q, then we can choose capital A so that the right-hand side that you see in the expression above is g of t. That is r squared plus pr plus q times capital A equals capital K. Now let's assume that we have sinusoidal forcing. That is, g of t equals capital K1 cosine omega t plus capital K2 sine omega t. We're going to recall the angle addition formulas in order to write our g of t in a slightly different form. That is, cosine of a sum of two angles, theta plus phi, is cosine theta cosine phi minus sine theta sine phi. Similarly, sine of the sum of two angles, theta and phi, is sine theta cosine phi plus cosine theta sine phi. Next, we're going to define capital A, capital K, theta, and curly theta as how you see here on your screen. Instead of worrying about exactly where all of this comes from, we'll just simply explain why these definitions are useful. First, observe that g of t can be expressed in terms of capital K times cosine omega t minus theta, with the same capital K and theta that you see above in the middle of your screen, using the angle addition formula for cosine. Now we're going to use this to help us find a particular solution for this sinusoidal forcing. Let's make a guess that our particular solution is in the form lowercase k cosine omega t plus lowercase k sine omega t. If this is the case, then we can compute y, its derivative y prime, and its second derivative y double prime. Putting all of this together, we then say that we have a constant times omega t plus a constant times sine omega t for the expression y double prime plus p times y prime plus q times y. We'll set these constants equal to uppercase K1 and uppercase K2, then use some of the definitions that we had on the previous screen to find that our lowercase k1 equals capital A times cosine of curly theta plus theta, and lowercase k2 equals capital A times sine of curly theta plus theta. So if we define phi as theta plus curly theta, then we find that our function y sub p of t, recall, was k1 cosine omega t plus k2 sine omega t, is equal to capital A times cosine omega t minus phi. In other words, whenever we have a sinusoidal forcing, we'll simply make the guess that our solution y sub p is lowercase k1 cosine omega t plus lowercase k2 sine omega t, and we can always solve for k sub 1 and k sub 2 in terms of uppercase k1 and uppercase k2. Now, we'd like to end today's lesson by giving some qualitative analysis of our solutions. That is, we'd like to discuss how the graphs behave once we have our differential equations. To this end, say that we have a second order linear equation in the form we've been discussing, where g of t now is a sinusoidal forcing function. We've seen that the general solution, y of t, can be expressed as k sub 1 times y sub 1 plus k sub 2 times y sub 2 plus a periodic function, capital A, cosine omega t minus phi, where capital A we can express in terms of capital K and omega. Similarly, phi we can write in terms of theta plus the arctangent of p omega divided by q minus omega squared. We'd like to discuss the qualitative behavior of the graphs of our solutions y of t. We have four different aspects we'd like to discuss. First is the idea of steady state response. By looking at the trace determinant plane, we see that the origin is a sink whenever p is positive. This is because our trace is negative p and our determinant is q. So this means that all homogeneous solutions for our second order equation, y sub h, must tend to 0 as time increases without bound. This means that all of our solutions y of t look like our particular solution, namely a cosine omega t minus phi for large times t. Next, let's take a look at the amplitude, capital A. We've seen that our particular solution, y sub p, is a periodic function, and all of our solutions, y of t, eventually oscillate with some amplitude, capital A. Notice in particular that this amplitude, capital A, actually gets smaller as the period omega gets larger. We'll come back and discuss this more later in future lessons. Third, we have the phase angle. Remember that if our forcing term, g of t, has phase angle theta, then our solutions, y of t, approach the particular solutions, y sub p of t, which have phase angles phi. In fact, in general, phi is different from theta. You can actually check that phi minus theta is the arctangent of p omega divided by q minus omega squared. Again, we'll come back and see this in future lessons, what happens when the forcing phase angle, that is the angle theta for g, is different from the solution phase angle, that is our angle phi. And finally, we can discuss the period. Notice that the period of both the forcing term g of t and the solution y of t approach the same quantity, namely capital T is 2 pi divided by omega. This period can actually be read off from the graph as follows. In the interval from 0 to 2 pi, the function y of t repeats omega times. Let's discuss all four of these concepts by looking at a couple of examples. For our first example, let's consider the second order equation y double prime plus twice y prime plus 2y equals sine of t. One can compute that a particular solution, y of p, is negative 2/5 cosine t plus 1/5 sine t. You can see a plot of the various solutions y of t here on your screen. You'll notice that it actually doesn't matter where the graph y starts. Eventually, all of the solutions behave like y sub p of t. This is the idea of having a steady state behavior. First, notice that the amplitudes are capital K equals 1. Indeed, this is because g of t is sine of t, and capital A is 1 over the square root of 5. This is by looking at y sub p of t. You can see that the graph here oscillates between plus or minus 1 over the square root of 5 for t large enough. Indeed, the square root of 5 is just a little bit over 2, so that means that our graph oscillates just below plus or minus 0.5. You can see this in terms of the graph here on the screen. Finally, the period capital T is 2 pi because our plot y of p repeats exactly once, that is omega equals 1, for t between pi and 3 pi. As a second example, let's consider the second order equation y double prime plus 2y prime plus 10 times y equals 4 cosine 2t. One can check that a particular solution, y sub p, is 6/13 cosine 2t plus 4/13 sine of 2t. Our amplitudes are k equals 4, indeed g of t is 4 cosine 2t, and capital A is 2 over the square root of 13. This comes from the y of p you see here at the top of the screen. Since the square root of 13 is just less than 4, then we see the capital A is just above 0.5. You can actually see here on the screen that the graph oscillates between plus or minus roughly 0.5 for t large enough. Notice that it doesn't even matter what our initial value of our solution is, that eventually all of our solutions behave like y sub p, which is just the graph here that's a periodic function. Finally, notice that the period capital T is pi because the plot of y sub p repeats twice, that is omega equals 2, for t between pi and 3 pi. Thanks very much for watching.